Camera action! Alright, welcome to another exciting episode of Advanced Level Chemistry here at Spain Park. Today is Wednesday, October the 5th. I'm in the park, November the 5th. Okay, time is flying. I'm not just a day late, I'm a whole month behind you. Okay, it is hard to believe that we are, just a few weeks away from Thanksgiving, which then takes us almost right into Christmas. We are almost finished with the first semester here. It's just, time is flying by. Okay? All right, so up until this point, this year's we did all the measurement and data and all that kind of stuff, and then we looked at just classifying matter into elements, compounds, mixtures. We briefly looked at the three types of mixtures based on small, medium, and large, and they were three types of mixtures: solution, colloids, suspension, small, medium, large. Okay, and then we broke down elements. We know the periodic table. We just did our element project, which I have to just look at. Hopefully this week I'll get to some of that. We need to get it up on the wall. Have our elements. Okay, that's the smallest, simplest. What's the smallest part of an element? An atom. And then we just mentioned briefly about molecules, that two or more elements combining together will make a compound composed of molecules. But then we broke the element down and we looked at the atom, but we really just focused in on the nucleus. We saw the discovery of the electron by the cathode ray tube by J.J. Thomson. We saw the discovery of the nucleus by Rutherford with his gold foil experiment. But we just said the basics. We learned out about atomic number and mass number and how to calculate average atomic weight and all those things. Okay? But then we broke down the atom itself and looked at the nucleus and what makes a nucleus stable or unstable. And the answer to that is what determines whether it's going to be stable or unstable. Say that again. The number of neutrons. Too many or too few cause it to be, quote, radioactive. So we learned all about radioactivity. So we just went down deep, small into the atom, and then into the nucleus, the smallest part of the atom, the protons and neutrons and what makes all that up, and the radioactivity and the stability. Now we need to look at, well, how are the electrons arranged? What do you know so far? What were you taught in middle school? They're in rings or shells, right? And what determines how far away it is? It's energy. So they're in energy levels. Okay, ladies, come on, focus. They're in these shells, okay? Energy levels. And how are the electrons moving in those shells? Kind of like an orbit, like the Earth around the sun is what you were taught. Isn't that correct? I hate to tell you this, but that is completely not correct. Okay? So we have to kind of figure out how the electrons really are arranged. Are they in energy levels, energy shells? Yes, but it's way more complicated than that. Okay? Now, the reality is that in order to understand the properties of electrons, we have to understand the properties of light, because we're going to find that all light, all EMR, all electromagnetic radiation is produced by electrons transitioning between these energy levels. So before we can really understand electrons, we have to understand the nature of light. And light has been a mystery for all of time. And it's still pretty much a mystery. Remember, I talked about the four fundamental forces of nature, the forces that just are. Number one was gravity. Why is there gravity? Well, we don't know. We can measure and describe gravity, but why is there gravity? We don't know. Okay? Now, we have the strong force and the weak force. Those are just forces within the nucleus. We talked about those. Keeps the nucleus from blowing apart. Why are those forces? What's going on? We don't know. We just know that it takes a strong force to keep the nucleus from blowing apart. So a very creative name, they just called it the strong force. But the fourth fundamental force of nature is this electromagnetic radiation, which I call EMR. Now, any type of wave that you can think of, except a sound wave, is an electromagnetic radiation. Now, goodbye wave, ocean wave, stadium wave, woo! Okay, it's almost started. Okay, okay. I'm sorry you did the wave with me. Okay, it was supposed to kind of go across the room there, but you guys didn't follow suit. Okay, So, but any microwave, sound wave, microwave, TV waves, radio waves, ultraviolet radiation, infrared radiation, visible light, gamma rays, X-rays, cosmic rays, any of those are all forms of electromagnetic radiation. Okay, we're going to look at the properties of that, and we're going to talk about how it, how it kind of works, but how it does it. It just does. It's one of those fundamental forces that we just know, let there be light and there was light. And it is a force that is, okay? So when we look at electromagnetic radiation, all EMR travels at the speed of light. And we know this is what we call C, and E equals mc squared. We're always gonna let C represent the speed of light. So in our study of light, we're going to understand the quantum mechanical model. This quantum, we're going to learn what the word quantum means, why it's called the quantum mechanical model, all of that. But the first thing that we're going to do today is we're going to look at light, electromagnetic radiation. Now you may already know some of these things, but if we look at a wave, first off, what do we call it? Well, this right here. Okay? This is called the origin. So if I was just doing a spring, if I stop putting energy in, this is where it's going to come to rest. So what do we call each of these peaks in a wave? It's called a crest. Very good. Got to be bold. Crest. What do we call the bottom ones? Trough. Okay? So what do we call the distance then from crest to crest? That's your wavelength. And we use the Greek letter lambda to represent it. Now, if you look right below here, here's wavelength. This is what a lambda is supposed to look like. My drawing is not very good. Okay? But that's what a lambda is, kind of like an upside down squiggly Y. That's your wavelength. Now the reality is, okay, what do you think wavelength is? Okay? Let's break the word down. Wavelength. Length of the wave. Okay? Now, we generally measure crest to crest. But what do you think a wave actually consists of? What is a wave? What are we measuring? Okay? It's really going to be a crest and a trough. So this is one wave cycle. Okay? Now you can be any equivalent point. Okay? So we're going top of the crest is going to be the exact same distance as from here to here. So it's just easier to draw the lines crest to crest or trough to trough. Okay? Now, what do we call this distance from the origin up? What's that going to do? Nobody?
What is the starting?
It's one of the words down below it. That's your amplitude. So in light, how do you think the amplitude, if you change the amplitude, what are you going to change about the light? The brightness of the light. Just like in a sound, the amplifier, you crank it up with the amplifier, it amplifies the sound. That does, when you put it on a microphone, is it supposed to change the tone or the note that you're singing? It's not supposed to, unless you know what auto-tune. A lot of the singers use the auto-tune because they really can't sing. They don't make an auto-tune strong enough, good enough, sensitive enough, with enough variation to be able to make me sound good if I was to try to sing. But it's not supposed to change. It's not supposed to change the note, so here the color. So if I increase the amplitude, if I go Okay? Did I change the wavelength at all? Okay, Anderson, y'all. Have I changed the wavelength at all? No. So has the color of the light changed at all? No. All I've done is made the light brighter. Whatever color this is, I just made it brighter. Okay? So that's wavelength. Okay? And then the last thing is the frequency. The frequency is how many wave cycles will pass by. Let's just say I randomly picked that spot right there. And the wave is traveling this way. The frequency is going to be how many cycles, how many crests, how many troughs pass this point in a second. And frequency uses, now, back in the day when I first did these notes, I used F a lot for frequency just because it made more sense. But most books now, they all use the Greek letter, which is, it looks like a V, but it's the Greek letter nu, N-U. So we're going to use nu in our equation. So if I'm looking at this, and then I go and I put a different wave, and I'm just going to kind of do here. Okay? Oh, swing and a miss. Okay? Now, if both of these waves are traveling at 3.00 times 10 to the 8th meters per second, which, by the way, is very, very fast. That's 186,000 miles per second, which means it's 7.5 times around the surface of the Earth in a second. But how long does it take light to get to us from the sun?
8 seconds.
Not 8 seconds. 8.3 minutes. So if the sun blew up right now, 8.3 minutes, we'd see a bright light, wow, and then we'd go see the light. Okay? We'd all die.
When do you think we would die?
Almost instantaneously.
No, like in the 8.3 minutes. When did we die before?
No.
Okay.
Because the heat wave, everything's traveling at this 3.00 times 10 to the 8th. So the light and the heat and everything else are all going to get, and the radiation are all going to get to us at the same time, and then we're all just going to fry. It's going to be way bigger than any atomic bomb. Now, I'm not worried. Suppose we become burned for another million years or so before any of that happens. So I know I'm old, but I don't plan to be that old. So it's traveling super fast. Now, little tidbit. So if lightning occurs, okay, we're supposed to maybe have some storms this weekend. Well, I hope. We need the rain desperately. Okay? But if we have lightning 3 or 5 miles away, if it's traveling at 186,000 miles per second, how long does it take us to see the lightning 3 miles away? Milliseconds, okay? I mean, fractions of a second. 186,000 miles in a second, 3 miles away, it's going to be way less than a second for us to, we're going to see the lightning instantaneously. But sound, it's a different type of wave. It's a mechanical wave. It travels through it needs a medium to travel. Light does not, which is going to be the mystery, one of the things we're going to talk about. Sound takes 5 seconds to go a mile. So you can find out how far the lightning is away by some people say you just count every second a mile, but it's not. Every 5 seconds is a mile between the lightning and the thunder. Okay? So, if you count 10 seconds from the time you saw the lightning to the time you first hear the thunder, it's about 2 miles away. So you just kind of give you an idea. Now, one little thing too. Lightning kills a lot of people every year, okay? Because people just aren't nearly afraid of it enough. And lightning really doesn't like rain. So the lightning a lot of times strikes out in front of the thunderstorm, which is why in football and any outdoor sport, if you have a lightning within 10 miles, okay, you got 30 minutes because you got to wait until that storm passes, because even though it's not raining, that lightning can come out of those clouds anywhere. Okay, so you're supposed to have, if the lightning is within 10 miles and everybody outside, any coach outside, and when I coached tennis, I had this, we have a lightning alert on our phone, and then that starts a timer, and you're supposed to go 30 minutes. Now I know that we don't all follow that.
So say I'm outside, I'm walking with a board, and he gets struck by lightning. What does that look like?
Well, first off, if you're even close, you're both going to get struck. But number two, the lightning comes in, what's going to happen, well, I mean, I don't know if you've seen a tree that gets struck, you can see the black streak all the way down it, okay? It's going to be a bright light, and you're going to hear the thunder immediately, and the concussion is just going to be overwhelming from the sound. Number two, the hair will stand up on end because of all of the static electricity in the air. Number three, if you're getting struck, you're going to get, it's going to be like, I don't know if you've ever been shocked by a plug or anything, but I mean, it's just going to be that on steroids. It's just going to be mega. It's going to affect your heart. More than likely, if you get hit, your heart's going to stop, and or at least get thrown out of rhythm, because everything's electrical. You basically, your nerves get fried. It's not good. You don't want that to happen. Okay? Now, golfers, if they're out in the rain playing and get struck, sometimes it'll travel along in the water. Like Lee Trevino got struck by lightning. Okay? He's a professional golfer, probably in the Jack Nicklaus. Do you guys at least know who Jack Nicklaus is? He was in Jack Nicklaus' day. He was another golfer. He's a very big personality golfer, but he was out, but it struck pretty far away, but it traveled through the grass, and so he only got a mile, but it still knocked him off his feet, and I think he still had to go to the hospital and all kinds of stuff for that. There's enough energy in a lightning bolt to power the entire city of New York, to power New York City for a day, if they could harness it. One lightning bolt. Okay? All right. Yeah, how many times, now I'm all this is not, I'm not supposed to be talking about all this. How many times do you think lightning strikes the earth? How often? What's the frequency, you think?
Once every second.
Okay?
Once every fraction.
100 times a second. Lightning striking the earth somewhere. 100 times a second. Okay, that's why so many people get killed. All right, now back to this, okay? Now listen, as interesting as that is, I know that I got the energy up here, but we got to refocus, okay? So here's the frequency. These two waves are traveling at the same speed. All EMR travels at the same speed, 3.00 times 10 to the 8th meters per second. So which one, if I'm counting how many are coming by this point right here, which is going to have more crests or troughs go by in a second? This wavelength or that wavelength? The bottom one, right? Because they're a lot closer. So what's the relationship then between wavelength and frequency? The longer the wavelength, what does that mean about the frequency? The shorter the frequency. So what type of relationship is that, direct or inverse?
Inverse.
That's the inverse and proportional. As the wavelength gets longer, the frequency gets shorter. Okay? The equation that relates that is right down below it. Okay, hopefully you drew all this in. All of this was supposed to be in that space right there. Hopefully you drew it all in. This is the only fill-in part of these notes. So when we look at the properties of a wave, okay, the longer the wavelength, the lower the frequency. We're going to go C equals lambda, and we really need to say C. This is the version we're going to use right here. C equals lambda nu. Okay? And again, what does C represent? Now this relationship is true for any wave, even sound waves. Wavelength times frequency always equals the speed of the wave. Now sound travels based upon the sound. It'll travel at different speeds, but wavelength times frequency is always going to equal the speed of the wave. All EMR travels at the speed of light, 3.00 times 10 to the 8th meters per second. Okay, so that's that relationship. Now, turn the page. This is where things start getting a little bit different, okay? In a sound wave, if I crank it up, Y'all remember in Back to the Future? Have y'all at least seen the original Back to the Future? Okay. What's the character's name?
Marty McFly.
Marty. Okay. When Marty, ladies, come on. When Marty goes and stands in front of the speaker at the very beginning of the movie and he plays the electric guitar, what happens? He gets thrown back, right? Because in sound, if you increase the amplitude, you increase the energy of the wave. But Max Planck, way at the turn of the century, 1900s, okay, he was playing with fire. He's a classic male. Now you know the iron skillets that you make cornbread in? Imagine a sphere made of that stuff, just a black iron skillet. And you put it into a fire. It's going to start to get hot. How are you going to know it's really hot? What color? It's going to get red hot, right? Oh man, that thing's red hot. Our team is red hot. That used to be a cheer. My sister was a cheerleader in high school. They used to, our team is red hot. I can't remember what the next line was. But anyway, so he would be able to put it in the fire, but somehow or other he knew that he was able to measure the temperature of the fire, measure the temperature of his sphere, and he found out that as it got hotter and hotter, it started changing colors. It went from red, and then it kind of got an orangish glow to it, and then if you got it hot enough, it would glow white hot. Now, any of y'all been putting LED lights into your home at all, replacing the light bulbs, putting LED? When you go and buy an LED light, some of them even have, like if it's a recessed light, you can adjust the color of the light. And they call it by temperature. You can have 2700K. That's going to be more of a yellowish color. Then you can go to 4000K, and it's going to be more of a bluish kind of color. Or you could go to 5000K, that's kelvins, and you're going to get more of a white. I just had to replace the fluorescent light bulbs in my closet, and we went with a 5000K LED light because it's a bright white and it gives the true color, so you can tell, are those navy pants or those black pants? You can kind of see, it's bright enough to be able to tell the difference whether it's a navy or a black, okay? Whereas some of the old duller lights, you got to take it out and kind of hold it up in the sunlight to be able to tell, is that navy or is that black, okay? That's what here. This is black body radiation. That's your cast iron, 6000K, you're going to get continuous spectrum. Okay? Now, listen, here, this is the important thing. Max Planck found that the energy of light is related to the frequency, not the amplitude. Now that was crazy because if light's a wave, it's supposed to be related to the amplitude. Up until this point, they all thought light was a wave. Well, actually, not everybody. Newton, you guys have heard of Isaac Newton, right? He did the laws of motion. Anything that goes in motion is going to stay in motion in the present state unless acted by an outside force. Well, Newton said, well, light must be a particle because it travels in a straight line. Waves kind of spread out. Okay, so he said it must be a particle travels in a straight line. If I throw a ball against a wall, it's going to bounce at a certain angle. If I shoot light at a mirror, it's going to bounce at the exact same angle. But then he said, the reason why light bends, and now you guys know that if you wear contacts or glasses, the whole reason, the way the glass works is that if you are nearsighted or farsighted, the light is either focusing, and it goes into your eyeball, and by the way, you know that the pupil, the black part of your eyeball, is nothing more than a hole, right? That's where the light gets into your eye. It's really just a hole. So when the doctor's looking in your eye, he's looking through your eye in the back of your red. As a matter of fact, if you take a picture and you get red eye, that's actually the blood on the back of your eyeball that's making it red. That's the retina shining through. So you're supposed to have an indirect light, so because it's the light going in and then bouncing back off your back of your retina that's being picked up by the film. So that's why red light reducer, they make the flash go 3 times because that's going to make your iris constrict, so less light can get into the back of your eyeball, and so it's there. So your eye your eye is just really just the pupil is there. So it's just kind of the crazy thing is that I forgot even where I was going with that. I got distracted by whatever. So the energy is thought to be, oh, I know what it's talking about. So your glasses, they bend the light. The bending of light is called refraction. So it bends the light to where it hits in front of your retina or it's focusing behind your retina. Okay, so that's what happens if you're near farsighted. So the glasses adjust it so it focuses right on the retina. That's what your contacts do. And so that helps make things not blurry, depending upon how off, it's all based upon the shape of your eyeball. And so how off it is the prescription that you have to have for your glasses or your contacts. Okay, well, Newton said light bends when it goes through a different source because it's speeding up. When it goes into water, you know how things look like they bend when they go into water? He said it's because of gravity, the light speeds up. And so he could explain light in terms of a particle. But a young whippersnapper about the same time came along, Christian Huygens, and he said, no, light's a wave. And he was able to explain how light could travel in a straight line as a wave. He explained reflection off a wall like a wave, but he said light is going to have to travel more slowly in water, not faster. Newton said faster, Huygens said slower. No way to measure it. That was late 1600s, early 1700s. It wasn't until much, much, much later that they found out, there's interference patterns, there's diffraction patterns. Everybody put the glasses on. Look up at the fluorescent light bulbs. Okay? Here. You're not there.
There we go.
Okay? All right. So when you look up there, you're seeing a rainbow. You're seeing a continuous spectrum. Well, up until Max Planck, okay, that's called a diffraction pattern. Okay? These glasses, that little plastic, actually has 5,000 tiny little slits for every centimeter. And those little slits cause the color to be separated, the light to be separated into all the different colors. Okay? It's a diffraction pattern. That's strictly a wave characteristic. Interference patterns were discovered. That's strictly a wave characteristic. So the wave properties started taking hold. Then they were able to calculate the speed of light. Now it's kind of interesting the way they did it. They had two mountains. The very first time they got the speed of light. And they had some person sitting up here on this mountain, and he was staring through a telescope at a mirror. Whoops. Okay? And they would shine the light on the mirror, and it would come back, and these mountains were 22 miles apart. Okay, now you can see why I know I should be an art teacher with this. It's so good. Okay, and they were able to shine the light. And so they got it lined up perfectly where 22 miles they could see the light. But then they began to rotate this. And when they rotated it, the light started shining off so they couldn't see it. But it needed to rotate 1/8 of a rotation. And then this one got to be there, and then the light would shine back again. So as they spun it, they got it to where how fast do we need to spin it to where it looks like a continuous beam. In other words, the light is traveling 44 miles, 22 this way, 22 that way. How long does it take 1/8 of a revolution to make it a continuous beam? And they were able to get the speed of light pretty close to what we know it to be today. It's a pretty ingenious way to do it. Now, that still didn't answer the question as far as faster or slower in water. Okay? Now, a few years later, a guy named Albert Michelson discovered or invented a thing called an interferometer, whatever that is. But he was able to measure the speed of light in water, and it turns out the speed of light in water was slower than that in air. So coming into the 1900s, they thought that light was a wave, and that the energy, if you just change the amplitude, you could change the energy by any amount. Kind of like a trombone can slide into any note. Okay? But Planck, by putting a thing into the fire, found out, wait, the energy is related. Y'all listen to this. This is important. The energy is related to the frequency, and we need to write this equation. When you put it here, we're going to say E equals H nu. We're not going to use F. We're going to use nu instead. Okay? The energy is related to the frequency, not the amplitude. Now that was crazy because that's not normal wave behavior. And he said, do you guys know what a marimba is? Those of you in band, okay? You might be with your little tykes. You might have had one where you had all the little different colored metal plates, and you had a little mallet that you could hit it, okay, going up and down. Well, if you ever watch a halftime show with a band, they have the marimbas down front in the pit, okay, and the guys with the 4 mallets, which I can't believe how they can do this. The 4 mallets are playing it, but each metal plate has a different note. Just imagine that with like an infinite numbers of metal plates. That as you go up, if you just went, it sounded like one note went right into the other, but each note actually has its own little thing. Max Planck said that, okay, I look at this, it looks like one continuous spectrum here, but as the colors blend into one another, if you pick one color, one frequency, it's going to have its own specific energy. Energy is transferred in specific amounts. That's going to become very important tomorrow when we go through this, okay? Now, that's a continuous spectrum. What we find with the electron, though, is that we form these discontinuous spectrums. So again, when you look at this, put the glasses on, and we'll end the day with this. When you look at this now, do we see a rainbow? You should see, now look, you're going to see some stray light. You should see a very distinct red line. You should see a distinct teal, kind of a bluish green line. And then off to the side, you should also see, don't look right at the light, look over here to the side of the lights. Okay, and maybe even turn your head, you can go whatever. But you should even be able to see a purple line if you look closely. Right on the very edge of the spectrum, there's a distinct purple line. Okay, now you got to realize that these glasses cost about $0.25. Okay, when you're looking that way, you're seeing this. Okay, all right, we'll pick up with this tomorrow.